Salutations, indeed. Okay. So today I have these two proofs in mind, which are supporting proofs for some of our theorems in Dirichlet series. And then we will finish off the Dirichlet series section. And I think we should be able to get all that done today. Just to recap, so both of these are roughly about this constant and different transformations on it. So again, this constant is defined as, so we have defined it up here in the Dirichlet series section. Where was it? Right here. So this bold one is defined as this summation of all the basis vectors. So it's a summation of just all the basis vectors, and it satisfies this condition that all of its projections are 1. So in the sense that these are functions, it can just be thought of as the one function. But we've given it a different name because this is not the same as the multiplicative identity one. Anyway, so we have these two theorems that we want to prove to support our proofs in about Dirichlet series. So the first one is that if we take this number and we square it, so we take its convolution with itself, then that'll be 0. That's our first theorem. This is well known. In fact, this second one, however, is my own theorem, and I think we're going to start with this one because I actually am more familiar with the proof. Because I wrote it. Let me find this section. Okay, right here. So we want to prove that this constant, so 2 minus bold 1 inverse, is in A sub theta. So that means it has a particular growth scheme so that it doesn't grow too quickly. And we're going to do this in a pretty roundabout way. We're going to essentially, what we want to do is we want to we want to find a form that's going to make this calculation really easy. So we're gonna calculate its theta value, or at the very least we're going to calculate a theta value that relates to it, and that will be useful to us. So the way that we can think of this, so the reason that this is valid, so we know that if we have 2 minus this bold 1, if we take this projection on the first index, so just to sort of establish this, if we take this projection on the first index, this is, so P1 is additive, or sorry, this should be inverse. If we take the P1 projection, so P1 permutes with the complex analytic functions. So in particular, since reciprocal is a complex analytic operation, then P1 of a reciprocal is the reciprocal of P1. So this will be P1 reciprocal of 2 minus this bold 1. And then also P1 is additive, so this is P1 of 2, which is 2, minus P1 of 1, which is 1. And this is 2 minus 1 inverse, which is 1. So we end up with P1 of this constant is 1. So in particular, it's a unit. So this is the first part. So it is a unit, in case we're worried. So we can take the reciprocal. Or sorry, I guess we should have been doing P1 of 2 minus 1. P1 of 2 minus 1 is 2 minus 1, which is 1. In case we're worried. So we want to put this into a different form, and we're going to do this in a really strange way. So we're going to introduce an idea that we haven't introduced before, and then we're going to essentially prove that there's this related object that that bounds the thing. Okay, so let's see. So we'll do this. So we'll say, so actually my proof on this is already pretty solid, but okay, so we first note that P1 of 2 minus this bold 1 equals 1, so it is a unit and the reciprocal is defined. Moreover, we have, so if we have 1 over 2 minus this bold 1, we can change this as 1 over 1 minus this bold 1 minus 1. Like this. So this is 1 over 2 minus bold 1, which is 1 over 1 minus, so this bold 1 gets negated, and then we have a double negative 1, so that's 2 minus bold 1. But then this is just this geometric series, right? So we have 1 minus 1 to the n, which is essentially it's positive on every projection. This is the wrong relation. So this is sort of our first note, is that this object is non-negative on every index. In fact, it's only 0 on the 0th index. This is because we have, so this bold 1 is 1 on every index. By subtracting 1, then we get this bold 1 minus 1 is 0 on the first index, and then 1 on all of the others, so it's positive. It's preceding 0. And then because we have this preceding 0, then no matter how many times we multiply it by itself, that will still be bounded below by 0. And then we're just adding all of them together, so it'll be positive. So now what we want to do is we're going to find an upper bound to this sort of sequence, to this object. We're going to find an upper bound which has a really easily calculable theta value. So we're going to define, so what we're going to do, so we will define, okay, yeah, so an upper bound to our constant and show that it is in A sub theta, which will consequently prove the theorem. So we'll define, inductively define B in A as follows. So the definition will be an inductive definition, so we'll have P sub k of B as being defined as equaling 1 plus the sum from k equals 2 to n of P sub something of B, and that something is the floor of the fraction of n over k. Okay, so we will prove that we will prove that 2 minus math baby m1 inverse is bounded by B, and that theta of B is less than infinity, which proves will prove the claim by the monotonicity of theta. Okay. Okay. So this is what we want to do. So we want to prove that this B is an upper bound. And we've selected this B very carefully. I couldn't tell you how I came across this. It was so long ago. But we're definitely starting at the end, so to speak. So we have this definition. So actually what we're going to prove, so given that, or rather here's what we'll do. What we will actually prove is that B is, so that we'll say this, P sub n of B is the sum of k less than or equal to n of 2 minus fold 1 inverse, which is projected on k. And the positivity of our constant inverse will prove. Is this correctly spelled? Yes, Overleaf just doesn't like it. Well, it's a word now. Okay, so what we're actually going to prove is that that piece of n of B is just equal to, so when we undo this inductive definition, we're going to end up with this. We can maybe restructure this so that this comes first, and then we end up proving this. Actually, yeah, let's do that. We'll do that. Okay, so let's do that instead. So define B in A, oops. Do I really? Oh wow, you're right. That's really silly of me. Wow. Well, it doesn't think that one's a word either, but now it is. Okay. Okay. Okay, so we're going to define, where are we? Okay, so define B and A to satisfy cat in a box. I love that. That's adorable. Okay, so define B and A to satisfy this relation. So, or rather, let's just put this on a line. So we've got is a sum across n and naturals e sub n k equals 1 to n of this. So the positivity of this constant proves that this constant is bounded by b. So, or rather, we can have 0 is bounded by this, bounded by b. So as long as that's not what I want. Theta b is less than infinity. The theorem follows from 1 to c of theta. Okay. Yes. So to prove this claim, we will find an inductive. Rather, we will prove. What do we want to do? There's a lot of really interesting calculations here. Okay, so yeah, there are a lot of interesting. Okay, so there's probably an easier way to prove this. So I do have a proof here. I'll show you what the proof looks like, what our current proof looks like that I did originally. So we start out by defining this b sub n using this inductive definition. And then we prove that this b sub n is the same as the b sub n we have over here. So we prove that these are the same. Then the proof that it's an a sub theta essentially follows from well, we do it by an induction, essentially. So once we have this inductive definition, then this is just sort of b sub n is just this summation of the b's below it, but using this weird sort of inverse scheme. And we just prove that when you sum all these up, they just end up really nice in an induction. It's hard to, I guess, we're just gonna have to figure that out. Maybe this is the only way. Anyway, so there's lots of interesting floor calculations here. So that's essentially what we're working towards. Okay, so now consider, actually let's call this, instead of calling this first one B, let's call this let's call this alpha. I don't know, because why not? This be this inverse. I'm gonna do piece of k of a. Okay, so we've given this constant that we're working on a label. We've just called it a. And we're giving this cumulative thing a label as well. We're calling this one alpha instead of b. So the positivity, so since 0 bounded above by a, then a is bounded by alpha. So as long as theta alpha is finite, then the claim follows from non-infinity of theta. Now consider I'll also consider b and a defined using okay, so we are going to define b this way. Okay, so we will prove that b equals alpha. So that's our plan. So we've got our alpha defined this way. Since 0 is a is bounded below by 0, then a is also bounded above by alpha, since we just sum up alpha, including up to Pn of alpha. And then we're going to prove that theta alpha is finite. But we're also going to consider b in a defined inductively as follows. So it's defined inductively on the projections, and it's defined this way. So we'll make a note. This inductive definition is valid since if k is strictly greater than 1, then n over k is strictly less than n. Okay, we will prove that b equals alpha. Okay, so to prove that b equals alpha, so to do this, it is enough to show that p sub n of b minus p sub n minus 1 of b equals p sub n of a. So since alpha is we're just summing up all the lower indices, it's this property is satisfied by alpha. So this is sort of here we're taking this sort of cumulative sequence, but here we're taking the difference, the concurrent difference, which is the inverse operation. So it's enough to show that this is the case. So in order to do this, so we'll just sort of work this out and see where it goes. So okay, so so we're going to prove that b is alpha, and then we'll prove that theta b is finite. So we're going to show that this consecutive difference is the same as a. Okay, so let's just sort of work out this difference. So we'll just start. So we have p sub n of b minus p sub n, p sub n minus 1 of b. So we just do this definition. So these ones in the inductive definition of b cancels out. So we end up with this summation for n, and then we subtract this other summation, and we just have to replace n with n minus 1. So we start out with this. Next, so we are going to define, okay, so what we want to show, so for our first modification, we notice that, oh sorry, let's actually combine these summations. Oh, hold on. This should also be n minus 1 here, shouldn't it? Okay, so this difference. And then let's also pull out this one when when k is n, which is p sub 1 of b plus, and then we have both of these summations, but where the first term is only going up to n minus 1, and then we combine the sums. Right, so we take the inductive definition. Since we're subtracting these, this 1 cancels out. And as we do the subtraction, we have different indices with different indexing for this sum. So we just pull out this n term here, and then we combine the summations like this. So we notice that if we have if this is equal to this, so we notice that if we have these two floors being equal, then the summing cancels out. So if this floor of n over k is equal to this floor of n minus 1 over k, if these are equal, then the summand will vanish, so it'll cancel out. Since then we'll have this expression will be the same as this expression, and we're just subtracting them off. So the thing that we want to observe is that if this fails, but rather if this is not the case, then we have, so what we want to show is that this floor of n minus k is equal to this floor of n minus 1 over k plus 1. Sorry, we actually have, then we have k divides n, and also this. Okay, so how do we prove that this is the case? Well, we could do the floor calculations if we would like. Okay, we could prove this. I'm gonna leave this here for now, and maybe we'll come back and flesh it out in a minute. But we can just sort of leave that here for now. So this lets us, this shouldn't be a new line. So we can modify the sum above. Okay, so then we get so whatever was above, so we start with that. So we have this same, where were we? This whole summation, so P1B and so on. So what we're saying is that if this summation doesn't cancel out, then these will be equal, and also k divides n. So, or rather, I guess what we want to say is yeah. This is not the case if and only if k is the divisor of n, and also this. Okay, so that lets us modify the summation. So if we have k going from 2 to n minus 1, then actually what we want to say is that so in going from 2 to n minus 1, we can instead say that k is a divisor of n, which is neither 1 nor n itself. So k divides n, but 1 is strictly less than k, which is strictly less than 1. Or sorry, strictly less than n. And in this context, we have this floor of where was it? This one. So we're going to solve for this. So this one's just going to be a floor of n minus k and then minus 1. So we'll replace this one. Or n minus k minus 1. This floor got clipped. Okay. Right. So just to be clear, so we'll flesh this out in a minute. The reason that this works is that this operation, floor of n over k, this is essentially figuring out what the largest number of k's will fit into n. If n minus k, if these two are not equal, so in particular, n over k is greater than n minus 1 over k, and floor is a non-decreasing function. So if this floor of n over k is not equal to this floor of n minus 1 over k, if these are not equal, then it must be the case that this floor of n over k is greater. It can only be greater by 1, so if k is at least 1, so n minus 1 over k can't be different by more than 1. So that if these are not equal, then they have to have this relationship. So this smaller one plus 1 gets this larger one. But also, if n over k is just barely fitting a certain number, if n is just barely fitting a certain number of k's in it, so this is sort of, we can think of this as Euclidean division. So if this Euclidean division works out to be just 1 larger than the one before it, then it must be the case that this is n is a multiple of k. Because if we go 1 down from a multiple of k, then we will lose a k that we can fit in. But if we're at something that isn't a multiple of k and we go 1 down, then we won't lose anything. We won't lose any k's that we can fit in. We can prove this formally, but we'll leave this here in a minute for now. Anyway, so this works out like this. So essentially we just take this summation. So we're saying, well, we're going through all k from 2 to n minus 1. But we're only going through k that divides n. And in the case where k divides n, we replace with this. So since we're going from 2 to n minus 1, then equivalently we have 1 less than k less than n, but also k is a divisor of n, and that just captures this whole summation range. So now that we have this, so since we defined, so remember, we defined these b sub n's. So let's see. Okay, yeah. So okay, so we've done this. So we've come out with this thing. So now what we want to say is okay, so now notice that p sub 1 of b is equal to 1. So this just follows out of the inductive definition. So if we have 1 here, then this will be a 1. 1 is less than 2, so this summation will be empty. And then we'll just have 1. So p sub b of 1 is 1. Or sorry, p sub 1 of b is 1. And yeah, so now notice that p sub b of 1, actually, let's just replace this here immediately. Okay. So now we'll do an induction. So now by induction, suppose that p sub, let's actually do, for all k less than n, we have p sub k of b minus p sub k minus 1 of b equaling p sub k of a. Actually, we want to say for every k less than n with k greater than 1. This is vacuously true when n equals 2, I think. Modify that. Okay, so so we're proving this difference thing happens to be Pn of a for every n greater than 1. So starting at n equals 2. So we're taking this inductive premise. So suppose that suppose by induction that for all k strictly less than n with k strictly greater than 1, we have p sub k of b minus p sub k minus 1 of b as being equal to p sub k of a. This is true vacuously when n equals 2, since there's no k strictly less than 2 with k strictly greater than 1. There's no integers like that. And then we have from this whole thing, we had this difference is equal to this whole mess here, which I'll start right there. N equals 2, and then since what we want to say is since n over k, or rather the floor of n over k oh, that's interesting, actually. Okay, so since the floor of n minus k is strictly less than n, or rather 1 is less than that, is less than n, for... Oh yeah, we could actually change this a little bit, instead of doing floor n minus k, or n over k. Let's actually just do, instead of floor n over k, since k is a divisor of n, we can just reverse the order of the summation to just do k, and then k minus 1. I think that's fine. Okay, so now by induction, suppose that for all k less than n with k greater than 1, we have this difference. This is vacuously true when n equals 2. And then we have, so we'll replace this with this, because I've just made that update. So we have p sub n of b minus p sub n minus 1 of b is the summation, but these are just p sub k, so this is by the inductive premise, this is p sub k of a, but then this is just literally the definition of, oh wait, hold on, that's not correct. Let me think on that. Oh yeah, actually this is fine, okay. This ends up being like this, and then we want to expand this out. So this is equal to 1 plus, or rather 1 minus, we have p sub 1 of a minus p sub n of a. So we have the top and bottom 1 and n. And then we add the summation n mid k, or k mid n, of p sub k of a times 1 p sub k divided by n of 1, since this is just 1. And then this ends up being 1 minus 1 minus p sub n of a plus p sub n of a and 1. That's correct, I think. Yes, so we start with the summation. We pull out these endpoints with this, and then this ends up being, so p sub 1 of a, yeah, we did verify p sub 1 of a is 1. We have 1 minus 1, and then these actually cancel out. Let's do an alignment environment here. Okay, so we do p sub n of this. So let's actually do, whoopsies. Let's actually do have this 1 minus 1 of this, but we'll just put a new line here. I think that should be fine. And then this is now, so this ends up being p sub n of a plus a m1, or we could equivalently write this as a times 1 plus bold 1. But then a, by definition, this was just so this is 1 plus bm bold 1 divided by a, so, or sorry, divided by 2 minus bm1, this. Okay, and then we can simplify this as, this is just, if we have, take the bottom, sorry, let's add in, oh yeah, let's, I think, is that right? I think that's maybe backwards. It should be negative p sub n of a. So this should actually be bold 1 minus 1. Minus 1. And minus 1 here. And then, okay. And then we can work from this. Okay, so what we have is we end up with, I think, we'll do -1, and then we'll do a +1 up here, which is to add this many. This bold one cancels out with this one, and we have 2 minus 1, right? This should end up being 1. Piece of n of 1 plus a, or sorry, -1 plus a, or a minus 1, which is piece of n of a. And this is going really far off of the thing. Okay, so we take this, so we do all this work to show that this B series has this definition, and then we do an induction. So suppose that for all k less than n with k greater than 1, we have this consecutive difference is p sub k of a. That's actually true when n is 2, which is where our base case is. And then we do this difference. So we take this, we substitute this out for p sub k of a. We account for these missing endpoints with this. Then this is just this convolution of a with this bold 1, since it's just this sum of cross divisors of p sub k of a. So this is 1, p sub 1 of a is 1, so we have -1, and then we have minus p sub n of a, and then plus p sub n of a times 1. These two cancel out, and then we combine these two to be this. And then this is just using the what a is by definition. This is just our shorthand for our constant, this one. So this is just bold 1 minus 1 over 2 minus bold 1. And then we simplify this fraction out to be -1 plus 1 over 2 minus bold 1. And this checks out. But then this is just a minus 1, which is p sub n of a, which follows since, so this follows since n is strictly greater than 1, so p sub n of 1 is 0. And that essentially concludes the induction. And thus follows my induction that p sub n of b minus p sub n minus 1 of b equals p sub n of a for all n greater than for all n strictly greater than 1, so integers n greater than 1. This is a pretty lengthy proof, isn't it? Okay, so we've proven okay, so we have this. Now we want to show that this proves that B is alpha. So this proves that B is alpha, since we can rewrite. So p sub n of B is a summation across k less than n of p sub n of, we'll do k equals 2 to n. So we'll do p sub 1 of b plus this, so this p sub n of p sub k of b So let's actually do this. So we have this difference, and then we'll say, since we also have this this condition for alpha for all n greater than 1, and since p sub 1 of alpha is 1, which is p sub 1 of beta, we can rewrite both as follows. So p sub n of b is p sub 1 of b plus the sum of differences, so p sub k minus p sub k minus 1 of b, which is then, the first term is 1. By the way, this is just a telescoping, sorry, that's not complete. There we go. This is just a telescoping sum when we do this. We just end up with, this whole summation is just p sub n of b minus p sub 2 minus 1, so p sub 1 of b, and then the p sub 1 of b cancels out. And then this is just 1 plus p sub k of a, which is p sub 1 of alpha plus this whole summation with alpha instead of b, and this is just p sub n of alpha. Very roundabout way to prove this form, but there it is. So we've proven that this form is valid. So we have this inductive form, and so we now have this. Since b is alpha, then there we go. So we've proven this whole mess proves that the consecutive differences of b is the same as just Pn of A. So we get this. But we also have this for alpha. So remember, alpha was just defined as this sort of consecutive summations. So if we take the consecutive difference of two alpha values, it'll just be the difference of these, whatever's left at the top, which will be this p sub n of A. And we also have p1 of alpha is 1, so again that just follows from this. Since we have p sub 1 of alpha is just going to be a sum from 1 to 1 of p sub k of a, so it's just p sub 1 of a. P sub 1 of a is 1, that's from this. And so p sub 1 of alpha is 1 as well. And we already know that p sub 1 of beta, sorry, this shouldn't be beta, this should be b. And we already know that p sub 1 of b is 1. And then we just use this telescoping sum, so we can rewrite anything like this, but then this is just equal to this, because we have these consecutive difference property, but then also 1 is p sub 1 of alpha, and again we have the consecutive difference property, so this is p sub n of alpha. Okay, so we have 0 is bounded below by a, which is bounded below by alpha, which is equal to b. We now prove that theta of b is less than infinity. So actually I have a much stronger result on the theta value of b. Actually we know exactly what it is. But I think that's maybe going to be hard to do. So let's see. Or rather, it won't be hard to do, but it'll be maybe a little unnecessary. Possibly. Okay. So let's see. Okay, maybe we do need to do this out sort of explicitly. Okay, so Okay, so let's do this. Okay, so we're going to prove that theta b is less than infinity. In particular, we're gonna prove something very specific. So, so what we're gonna do is we're going to say, consider the zeta function zeta of s, which is a Dirichlet series with 1 on s. Okay, so we're going to consider this zeta function as this. So notice that over real values are in 1 exclusive to infinity, exclusive, the zeta function is, sorry, let's actually do this. If we restrict r in 0, 1, the zeta function zeta of r is a strictly decreasing, or sorry, actually let's do this. Notice that for r in 1 infinity, we have zeta tending, sorry, zeta of r strictly decreasing, continuous, diverging at as r goes to 1, or rather specifically tending to infinity as r goes to 1, and tending to 1 as r goes to infinity. This is all very specific, but it's a thing. This is all important. So we're gonna have this zeta function. So we just observed that for real r in 1 to infinity, we have zeta of r strictly decreasing, continuous, tending to infinity as r goes to 1, and tending to 1 as r goes to infinity. It thus follows that there is a unique value theta in, let me double check, that's what we need. Yeah, okay. So there's a unique value theta in 1 to infinity such that zeta theta is 2. Okay, so essentially we're saying, since zeta is strictly decreasing, continuous, and tending to infinity at 1, and tending to 1 at infinity, it must bijectively cover all the values from 1 to infinity. In particular, since it's continuous, and since it's strictly decreasing, then that value is unique. So there's a unique value theta such that zeta theta is 2. Moreover, it can be verified numerically that zeta of, let me get this right because it's very finicky. Okay, it can be verified numerically that zeta of, what is it, log base 2 of 3 is strictly less than 2. So it must be the case, sorry, 2, which is equal to zeta theta. So it must be the case that theta is strictly less than log base 2 of 3. So this numerical condition we can maybe add, be a bit more specific. So we're saying it can be verified numerically that this is true, that zeta of log base 2 of 3 is less than 2. But maybe we want to make this calculation a little bit more specific, to sort of to sort of articulate exactly when this is true. So I think I'll also come back to this one and specify why this is true. But we'll come back to this condition in a minute. But what's important is that theta is less than log base 2 of 3. That's our premise. Okay, so given this, so this allows us to verify. So now, actually, finally, we notice the first 3 values of b as being b, p sub 1 of b is 1, p sub 2 of b is 2, and p sub 3 of b is 3. I think that's the case. 1, 2, 3. Yes. So this, again, this can follow from, we can just carry this out from its definition. So this can just be followed from this. So you can just use it from this inductive definition. So we're going to prove that theta beta is less than infinity. So so consider the zeta function. Notice that zeta is a bijection mapping 1 to infinity over to 1 to infinity again, and it's strictly decreasing. So there's a unique value, zeta theta equals 2, and by this numerical condition, we have to have theta less than log base 2 of 3. Then finally, notice the first 3 values. P sub 1 of b is 1, p sub 2 of b is 2, p sub 3 of b is 3. Let's separate these better with commas so it doesn't give us a nasty line break. Interesting. Okay. Okay, so now that we have all this set up, from this, we can thus have, oops. Okay, so we thus have, so p sub n, p sub 1 of b is 1. This is 1 to the power of theta 2, because if we raise power of theta 2, it doesn't matter, it's the same. It's always 1, if it's 1. So we got p sub 1 of b is less than or equal to 1 to the power of theta sub 2. We also have p sub 2, and this one's important. P sub 2 of b is 2. Which is 3 minus 1, which is 2 to the power of log base 2 of 3 minus 1, which is as we know, strictly less than 2 to the power of theta 2 minus 1. And that implies that p sub 2 of b is less than or equal to 2 to the power of theta 2 minus 1. Actually, we don't need this. These are redundant. Theta 2 minus 1? Okay. And the last one is p sub 3 of b is 3, which is strictly less than 2 to the power of theta 2 So again, we do have, yes, just from this, strictly less than 2 to the power of theta 2, which is in turn strictly less than 3 to the power of theta 2. Okay, so essentially what we're noticing is, and so I guess in advance I can just tell you, we're going to prove that the theta value of b is 2, or sorry, is theta, the theta that we've selected. Okay, so we want to make a last note. So lastly, we note that for n greater than 3, we can let k sub n be equal to the floor of n over 2, which satisfies, rather, by letting k sub n be equal to this, we have 1 less than for all n greater than 3. One less than k sub n less than n, and also n over k sub n, the floor of n over k sub n is 2. Okay, so lastly, by letting k sub n be this, for all n greater than 3, we have this, and also this. This lets us, so this is everything we need. This is all the preliminaries for our crazy induction. Okay, so we've got all our preliminaries set up. So now we're going to say, now by induction, suppose that for some n greater than 3, we have for some n greater than 3, we have that all k less than n satisfying p sub k of b as being less than or equal to j power theta 2. Which is true when n equals 4, as established. So this condition, so we're doing an induction, so we're going to show that p sub, sorry, that shouldn't be j, that should be k. So we're gonna verify that in fact p sub k of b is strictly less than or equal to k power theta 2 for every k. So that's actually what we're going to prove. So we're saying by induction, suppose that for some n greater than 3, we have all k less than n satisfying this inequality. So we know this inequality is satisfied with 1. It's satisfied with 2. Actually, we can do right here, this is strictly less than 2 power theta 2. This shouldn't be theta sub 2, it should be theta. Oops, I made a typo. Okay, so we're saying this is, so we're gonna say p sub k of b is less than or equal to k power theta. It's true with 1, they're equal. It's true with 2, strictly less than, and it's true with 3, they're strictly less than. We can maybe be a bit more specific actually if we want to. We can say this is equal to 2 power log base 2 of 3. Oh wait, am I dumb? Wait, hold on. I think I messed something up. Let me see. I think it should be theta 2. Oh yeah, I did get this wrong. It was, where was it? Right here. Log base zeta log base 2 of 3. This is supposed to be greater than. This is why we should double check our numerical premises. This is greater than. So theta is greater than log base 2 of 3. That's what we need. We can actually verify this right now, numerically. Well, it'll be non-rigorous, but log base 2 of 3 is log of 3 divided by log of 2. And we just take zeta of that and go into numeric mode. Wow, it's greater than 2. So there it is. By the way, so zeta of log base 2 of 3 is right there, strictly greater than 2. 2.327. It's a good thing that I double checked that. Okay, so it can be verified numerically that zeta of log base 2 of 3 is greater than 2, which as we know is zeta of theta. Since zeta is strictly decreasing and this is larger, it must be the case that theta is greater than log base 2 of 3. Let's reverse this inequality so that it looks more intuitive. So I'll put theta on the right side. So log base 2 of 3 is less than theta. See computer black square, yeah. Yeah. We'll maybe we could maybe do a little double check on that. But anyway, okay, so we do have actually proving numerics rigorously is actually kind of hard. It's like surprisingly difficult. Like you wouldn't think it would be hard, but it is. It's like really finicky. Like you just have to get. It's like, oh yeah, the computer says it's like clearly greater than 2. But like to verify this formally, I'm pretty sure. So first of all, we'd have to like numerically evaluate log of 3 and also log of 2, and then we're gonna have to numerically evaluate zeta. The benefit, I guess the part that makes this maybe a little easier is that we can because zeta is strictly decreasing, it's fine to you know, as long as we have a small enough % error, then this will just end up being fine. But yeah, because zeta is monotone and also log is monotone, so that makes it a little bit easier. But it's still, you know. By the way, log base 3 of 2 looks like this. It's about 1.58. So our theta is slightly greater than that. Actually, we can figure out 1.767.6. Oh, that's getting bigger. 7, 6, 5, 4, 3. Yeah, this seems about right. 2, 7, 9, 8, 9, 9. Oh, wait. 8, 5, 6. Yes, it's about 1.7287. Very rigorous. Very rigorous. This is our theta value, approximately 1.7287. Anyway, so we could maybe justify this a little more, but zeta of log base 2 of 3 is greater than 2, which is, as we know, zeta theta. So we must have log base 2 of 3 less than theta. So finally we mark on these first 3 values. That sets up our initial conditions for our induction. So we'll say by induction, suppose that for some suppose that for some n greater than 3, we have all k less than n satisfying this. So we do have this satisfies when k is 1, satisfies when k is 2, satisfies when k is 3. And since n is greater than 3, then this is vacuous. This is true when n is 4. Now by induction, okay, so we got these 1, 2, 3, and we've set up our premises. Then we have, so now we just take this inductive definition of B, and this is why we wanted to set up B this way, because this is very important. So we end up with this, so P sub n of B is the summation. And so the reason, by the way, that we need this K sub n is so that we can get rid of this plus 1. So we're going to rewrite this as, so this is, this whole summation is equal to so we'll do P sub K sub n of B plus, and we'll do K equals 2 to n, but we also want K is not equal to K sub n. So we've extracted the K sub n term out of the summation, is essentially what we've done. Let me see if there's a, oh yeah, let's do, I have a nice formatting here. I did a substack, I think, on my original draft. I forget how to do these. I think it's like this. Maybe. Oh yeah, it is, look at that. Okay, so K is 2, K is not equal to K sub n. So we've extracted the K sub n term. But we know that, so right here, we just have P sub, sorry, this shouldn't be P sub K sub n. This should be P sub 2. Because we know that the floor of K over K sub n, this one right here is 2. So P sub 2 of B, so we've extracted the K sub n term. But P sub 2 of B is strictly less than 2 power theta minus 1. And also by induction, all of these. So we get this less than or equal to, so you get 1 plus, and then 2 power theta sub 2 minus 1, and then plus the summation, it's exactly the same sum. But now we have, we're bounding this thing, P sub whatever of B, this is being bounded by whatever this thing is to the power of theta 2. Oh, sorry, not theta 2, it's just theta. I have renamed this. Okay, yes. So we've set up this inductive definition, which we have, and then we've pulled out the K sub n term, which gives us this, and then we bounded this with our premises. P sub 2 of B, this is bounded with this, so we get this. And then these just become this. Actually, let me fix these floors here. Actually, I'll do one better. I'll just get rid of these parentheses. And since n is a constant here, and theta is positive, this is in turn less than or equal to, so we get the minus 1 cancels out, this plus 1 cancels out with that, and here we get, instead of the floor, we can just do parentheses, right? So we just make a bigger thing by taking the floor away. Oops. There we go. Oh yeah, okay. Yeah, we're doing it. Okay, so this is this, and then we have, I just had to make sure that this would all check out. So this becomes, we get, let me see where this comes from. Oh right, because we do actually have, let me do that. before we remove the parentheses, or sorry, before we remove the floor. So we end up with this. So this is actually equal to, so this 1 cancels out, and this 1 cancels out. And again, this 2, we know that 2 is this 2 is just the fraction and over k sub n. Now it's important. I'm sorry about that. Okay, so p sub n of b, this is the inductive definition. We extract out the k sub n term. We do our inequalities like this. And then this one cancels out this one, and this 2 power theta ends up being this, which is just 2 power theta. And then this becomes, so we just put this, we just insert this back into the summation. So this is just the k sub n term of the sum. So we no longer have, removing this k sub n term. Okay. So we end up with this. Okay, now we have less than or equal to this whole summation, and we get k from 2 to n. Oops. Let me fix that. Okay, so get a 2 to n, and then this is just equal to n power theta times the summation k equals 2 to n of k power negative theta, which is less than or equal to n power theta times the summation k equals 1 to infinity of k power minus theta. But hey, that's just, sorry, let's do 2 still. Still 2. 2 to infinity, k power minus theta. But hey, that's just n power minus theta, sorry, n power theta times zeta theta minus 1. But then this is just n power theta itself, because zeta theta is 2. And that's it. That's the whole induction. Yeah, so essentially we just use this trick. So because we have this floor of n over k, especially if k is sort of in the region around about half of n, most of the terms, especially when k is large, is going to be around 1 or 2. So essentially we just say, well, pick one of these terms, pick out one of the terms from the sum for which this fraction, this floor of this fraction is 2, which there's actually a lot of them, but we're just picking this one. So pick out one of these terms where it's 2, use the fact that p sub 2 of b is strictly less than 2 power theta minus 1, and also that 2 power theta minus 1 is just this. So we have this whole thing. So do the inductive definition, pull out this k sub n term, do our inequalities, these ones cancel out, this 2 power theta turns back into this floor, which can then be put back into the sum, like this. And then this is bounded by, if we just don't do the floor and just have this, then this will be larger. So we just end up with this summation instead. And then this is just a simple analysis. We get n power theta times the summation times k power minus theta. And then by just letting this upper bound here go to infinity, we get this nice upper bound. This is bounded by n power theta times the summation of k power negative theta. But this entire summation is literally just zeta. of k, zeta of theta, but we're just missing this bottom term, which is just 1. So this is n power theta, which is this one, times this zeta theta minus 1. Zeta theta is 2, so this is just n power theta. And remember, our inductive premise was, suppose that by strong induction, p sub k of b is less than or equal to k power theta. And now we have this is true for n as well. So the induction follows for all n. Since we have, so theta, capital theta, of the sequence of n power theta, lowercase theta, in terms of n. This is just theta. Then capital theta of b is less than or equal to theta, which is strictly less than infinity. And the claim is proven. And that's it. So that's sort of the whole thing. It's very weird. It's very weird proof, very specific. I'm really not sure how to make it any simpler. I wish I could, because it's very complicated. It's stunningly complicated. In fact, it's much more complicated than I think one might expect. But that is that. So we get this. So this is nice. 2 minus bold 1 inverse is an a theta. Yes. Okay, so now that we've got this, I think we could maybe prove this one if we'd like. But I think actually I'm going to leave this for now, this one in this appendix, and we're just going to use this result right away, actually, to finish the section off for Dirichlet series. So we're right up here, so right around here. Okay, so let's actually do, let's actually put it before this lemma. Okay, so our theorem is, let alpha be in A sub theta and F be complex analytic at alpha, then F of alpha is also in A theta. So this is actually what we're going to prove first. So essentially what we're saying is that A theta is closed under application by complex analytic functions, which is very interesting, I think. So we're going to do this. So the way that this works is we're going to use the theorem that we just proved, actually. We're going to prove that our thing is bounded. So let's see here. Because this one was also pretty finicky. Okay, so we've got, okay, so we'll say, because we already got alpha. Let C sub n be, or rather, we'll say let C in C power n 0 be the coefficients of the power series, or sorry, the Taylor series. F of x is equal to the sum on n. We'll do C sub n times x minus p1 of alpha. The Taylor series for f centered at p1 of alpha. so that f of x equals this for all x in a, actually, we can say specifically in a neighborhood of alpha. I think we actually don't need that. We can actually just say that we can calculate. Let me double check on this, because essentially we just want to prove a number bound. Think on this. Oh, this is very specific, isn't it? I feel like this should be straightforward. This is very specific. Because we always have to just take out this first index over and over again, because it's very important. Let me see how this is essentially constituted. So I think what we end up doing, yeah, is we just bound this with a geometric series, essentially. We might need another lemma for this as well. Let me show you what I'm looking at. So this is the original proof for this one. So it's actually rather short. It's maybe shorter than we're going to end up having it be, which is maybe not what we want. But also it's very optimized for the language of that I had set up in this original draft. In particular, in this theorem we use a special constant, ID, and we also have this ODOT operation, which might mean that now is the time to bring that in. Because this will be a little hard to do otherwise. Let's see, A of C bounded by the absolute value an times I value this. Then we bound the C minus C1 by a thing like this, or times something like that, or power minus n. Oh, that's interesting. That's very specific. That's very finicky. We've bounded the absolute value of an with r power minus n. And we've also selected a theta such that we can make this coefficient be r. That's very interesting. Okay. And then this just gives us, so we pull this m, these r's out, cancel out, and then we get this. And then this is supposed to end up being this ID theta pointwise multiplied by this constant, which we know is an a sub theta. Okay. I think we're going to maybe have to do that. Essentially we're just saying Yeah, okay. So we're gonna have to get a little finicky about this. Okay, so let's do that, I think. We'll just do that. So we're actually gonna finally introduce this O dot operation, this circle dot operation. Right. Okay. Let me think on how I want to do this. Because we have all these nice theorems here. I don't want to interrupt the flow, but I also don't want to just relegate these to an appendix, because none of this notation is introduced in the paper. I think we just have to put it in, don't we? Because all of the machinery is required for this to go smoothly. Okay. So okay. Let's see what we've got. Okay. So we've gone up to the point where our function, our D is an isomorphism. That's fine. Okay, between A theta and D, a script D. And what we want to build up to is this. But to do that, we need some more helping things. Okay, so we could either introduce all this notation, or we could prove it a different way. Essentially, all we have to do, really, no, we actually definitely need to do this explicitly. There's no way to do this practically without. Okay, I'm just gonna have to do the notation. There's no way to do this proof without doing that. Okay, so we'll do it this way. So okay, so to work up to our last theorem, we need some more supporting tools. So we're going to define some operations. So first we introduce a binary operation O dot, which maps A times, oops, A to A as a pointwise product. So explicitly, we have for any xy in A, we define x dot y is defined as equaling the summation n natural e sub n p sub n of x p sub n of y. Okay. Okay, so immediately we notice that ODA is continuous. Finally. Goodbye. Okay. ODA is continuous. Okay, so along with this, we also introduce constants, a family of constants, and we'll say for each theta in real, let id sub theta, lowercase theta, be in A, defined as follows. So id sub theta is defined as equaling a summation, again n in n, of e sub n, and then n power theta. And then we'll say, notice that these constants all have, or we can say equivalently, id sub theta is just equal to the iota inverse, I think, inclusion of the sequence n power theta, such that n is in natural. So it's just a sequence of the powers of n power theta. So we notice then that capital theta iota id theta is theta. Also, that reminds me, that we are now using this iota operator. So actually we want to update the theorem that we just proved down here with that. Okay. So where are we? Right here. Okay, so we've defined this binary operation. This operation is continuous. We also introduce a family of constants, id theta, like this. So equivalently, it's just this sequence of theta powers. And then we're also going to introduce, lastly, we introduce a family, or rather a set of A defined as follows. Also, I think I made it, No, this is fine. Okay. Okay, so we're also going to define a special subset of R space. So we have A sub capital M is defined as equaling the set of, we'll do X in A such that for all nk in naturals, I think it's P sub nk of X equals P sub n of X, P sub k of X. Actually, we want to be specific. We'll say this is X in A star. Where were we? Right here. Okay. Oops. Okay, so we have a pointwise product operation, which is continuous. We have these family of constants, like this. And then we have this other subset of A. So this subset of A is the unit. Actually, we can just say, instead of saying X in A, we can just say X in A set minus 0. So just non-zero X. Such that for all of these indices, we have this. So these values X, like this, when considered as functions, they're called completely multiplicative. And then we can say, we also notice that each of ID sub theta is in A sub n. Okay, so this will support or rather, what do we want to say? We want to say what do we use? We use O dot distributes over. Okay, so what we're going to use this for is this will support our future theorems, or rather, let's say this. Okay, so the theorem that we have about this, about these things, is, we'll say, let Z be in A sub capital M, and XY be in A. Then Z O dot X plus Y is equal to Z O dot X plus Z O dot Y. So it distributes over addition. And Z O dot X star Y is equal to Z O dot X star Z O dot Y. And it distributes over Dirichlet product. So if we have an element in the set A sub m, then it distributes over addition and distributes over Dirichlet product with this O dot operation. And so that's what we want to say. So as for the proof, so the proof for distributing over addition follows, and it's actually really easy. So for addition, actually we'll say let n in n be any index. Then this follows, we just have p sub n z o dot x plus y is, so by definition this is p sub n of z, p sub n of x plus y, which is equal to p sub n of z times p sub n of x plus p sub n of z p sub n of y, but then this is just p sub n of z o dot x plus z o dot y. So it just follows from the distributive law for just real and complex numbers. Since it's just a pointless product, then of course it distributes over addition. So that one's easy. Okay. Okay, then for Dirichlet product, so we have this, so we have z o dot, so we'll do p sub n projection z o dot, and now we have, instead of x plus y, we have x times y. So this is just p sub n of z, and then times p sub n of x star y. But this is just, so we still have p sub n of z, this shouldn't be a backslash. And then we have the sum, where a, b equals k, and we have p sub a of x, p sub b of y. But we can just rewrite this, right, as, we can just rewrite this as, since we have p sub n, or sorry, it shouldn't be k, it should be n. ab equals n. But then we can just rewrite this as, well, ab equals n, so we just have p sub az, and then p sub bz, since it's completely multiplicative. Let's see if that runs over almost. Actually, we can say, we can be a bit more explicit with this. So we have this, so we pull in this summation p sub n of z, and then we have p sub az, p sub bz, and then we just rearrange that, so this becomes p sub az with p sub ax, and then p sub bz with p sub by, and then this is just z o dot x times z o dot y, and that's it. There should be an equal sign here. Let's also put our tabs here. And that's going to run over. Okay. And that's it. So So if we have something in a sub m, then O dot will distribute over addition and also distributes over convolution. So this is essentially what we need. So now that we have this, so this is very useful. So this is going to help us. We're going to use this with these ID thetas. Is how we're going to use that. Okay. So now we can do this lemma. So not this lemma. This one. Nope, not this one either. We didn't set up the theorem, did we? Yeah, okay. This one is the one that we should be working on, and it's right there. Okay. Okay. So here's what we'll do. So we'll say, oh yeah, there is a typo right there. Okay, fixed. Okay, so we have the Taylor series of f centered at p1 of alpha, which is a complex number. Okay, so now what we want to say, so since we have, actually we can just say find any r greater than phi of c, then we must have r greater than 5z, and we'll call it, actually wait, that's not right, is it? Let me double check. I think that is correct, actually. R greater than 5c and a constant, okay. Instead of using c, let's use beta. So find any r greater than 5 beta, and corresponding, we'll do b greater than 0 such that p sub n, this shouldn't be 5 beta, yes it is, such that beta sub n is less than or equal to, or this should actually be absolute value of beta sub n is less than or equal to b r power n for all n. Okay, so that's the first thing. Okay, so now what we want to do now we want to say, now find theta greater than capital theta of iota alpha which satisfies absolute value p sub n of alpha as strictly less than r n power theta for all n greater than 1. So this is really particular. So we're saying we want to find a theta which makes it so that p sub n of alpha is less than just r times n power theta. So remember, r is this radius greater than capital phi beta. So this is possible. So this is possible since this is possible since we can find some as of r, we'll say a greater than 0, such that absolute value p sub n of a is strictly less than r power rn power, sorry, not rn or n my words. A way less than theta. P sub n less than a power n theta. Okay, let me think on this. So the reason that we can select this is we can say this is possible since let me think on how I want to formalize this. Okay, I think I've got what we want. Okay. Okay, not this one. This one. So we want to find a theta which satisfies this. So, finding such theta is possible since by the second characterization, every theta strictly greater than capital theta of alpha, or sorry, iota alpha, so this is possible since by the second characterization, every theta greater than this has, we'll do p sub n of alpha times n power minus theta goes to 0 with n to infinity. So in particular, there is always a point at which, actually we can just say there is a point and capital N0 after which absolute value p sub n, or we can say, yeah, absolute value p sub n alpha n power minus theta is strictly less than r, so that absolute value p sub n alpha is strictly less than r theta. And then we can say, since we have, since for all n and less than n0, actually let's do it this way. So finding such theta possible since by the second characterization, we can say every theta prime greater than theta has p sub n minus theta prime going to 0 and n to infinity, so in particular n0, after which p sub n alpha n power minus theta prime is less than r, so that p sub n alpha is less than r n power theta prime. Since for all n less than n0 we have r n power theta prime going to infinity as theta prime goes to infinity. Then in particular n less than n0 with n, actually we can just say, since for all n greater than 1, we have Rn power theta prime going to infinity as theta goes to infinity, and we can take theta prime, takes theta strictly greater than theta prime. Actually, let's do this. So find such theta as possible since with the integration. We'll do every theta 0 greater than theta alpha, blah blah, has, so theta prime will do theta 0, particular after which theta 0 is less than that, so then this is less than that. Okay, since for all n greater than 1 we have Rn power theta going to infinity as theta goes to infinity, we can take theta greater than theta 0 large enough so that Rn power theta is strictly greater than p sub n alpha, or absolute value p sub n alpha, for the finitely many and having 1 less than n 0. After which n greater than or equal to n 0. I have this, so that this is that. And greater than we have this. Okay, so theta greater than theta 0 large enough so that Rn power theta is greater than this absolute value for the finitely many, and with this. It follows then. Actually, this is fine. Okay, so what we're saying is, we're saying, so we're going to take these coefficients for the Taylor series. We're going to find an R greater than capital Phi beta, and then any bounding coefficient. This B doesn't matter. The R is important. The B is just the bounding coefficient. So absolute value beta less than or equal to B Rn for all n. Then we'll find theta greater than capital theta iota alpha, which satisfies p sub n of alpha less than this for all n greater than 1. Now find this lower theta, which satisfies, so p sub n alpha is strictly less than r power n theta for all n greater than 1. The reason this is possible is since, in particular, if we just select theta 0 greater than theta iota alpha, then we do have p sub n alpha times n power negative theta 0 going to 0. This is by the second characterization. So in particular, since this goes to 0, there's a point n0 after which n greater than or equal to n0 have this absolute value p n alpha n power minus theta strictly less than r. This follows since r is positive. So then the absolute value of p sub n alpha is strictly less than r and theta is 0. Since for all n greater than 1, we have r and theta going to infinity as theta goes to infinity, then we can take theta strictly greater than theta 0. Okay, we can maybe do this another way around, actually. Let's do it this way. We'll say select any theta strictly greater than capital theta iota alpha. Then from the second characterization, yeah, we just take r to be really large. Yeah, so from the second characterization, we have, we can say there is some r greater than 0, sorry, this is the third characterization. There's some r greater than 0 such that absolute value p sub n alpha, sorry, yeah, p sub n alpha times n power minus, sorry, f sub I percent less than or equal to n power r times n power theta. Is that what I'm trying to say? For the third characterization, r greater than 0 such that less than or equal to r times n power theta. Okay, yes. For all n. Okay. Without loss of generality, so we may assume that r is greater than capital phi of beta. I think this is okay. So when we select r large enough to assume that r is strictly greater than phi beta. So we just have r greater than phi beta, and then we've selected theta such that this is less than that. Okay, that's fine. So that's actually what we needed. Okay, so we've got that. Now, I think we just bound this with so equivalently, you may say that A of alpha minus, or sorry, A of alpha is bounded by R ID sub theta. If we subtract off the first index, then also we can say, and this is important, this. Okay, so to summarize, we're saying beta are the coefficients of f. Select a theta greater than theta iota alpha, and then this r greater than 0 such that alpha is bounded by r and theta. Without loss of generality, we're also going to select r large enough to assume that r is greater than phi beta. Equivalently, we can say that A of alpha is bounded by r times id theta, that is r times n power theta on each projection. If we subtract off the first index, so we have this inequality. If we just kill the first index of this by just subtracting p1 alpha, we can also kill the first index of this, and we'll still have this inequality. So if we just subtract off the first index, we get this inequality instead. So this is useful. So this lets us take, so I think now we can bound f of alpha as follows. So we have, let's put this in a line. So we have A of f of alpha is bounded by, so we have the summation n equals 0 to infinity. So again, the coefficients of alpha are absolute value, so we have beta sub n, and then we have A of whatever we bound alpha by, alpha minus p1 alpha, which is this. It'll be this to the power of n, and then the r's cancel out. Or sorry, we want to do A of alpha minus p1 of alpha power n. We'll just do this in parts. And then this is in turn bounded by, so instead of beta, we'll do, actually we forgot to do our constant for the beta. So we'll select r large enough, large enough to assume that this is this, and then we have b greater than 0 such that absolute value beta sub m is less than or equal to so we're going to select b greater than 0 such that beta n is bounded by b times r power n. Okay, that's our constant. So b times r power n. Okay, so we're saying beta are coefficients, Taylor series, so that f is the summation. Select theta greater than iota, theta iota alpha, and then the third characterization is r greater than 0 such that this. We may also select r large enough to assume that r is greater than phi beta, and then we have b greater than 0 such that absolute value beta is bounded by b r to the n. We may also say that absolute value alpha is bounded by our id theta, so that's just this, but stated differently by each index. And then by subtracting the first index, we end up with this. We can now bound f of alpha as follows. So we have a of f alpha bounded by, so we just have the summation. So we get absolute value beta n times absolute value alpha minus p1 alpha power n. And then this is bounded by, so beta is bounded by b r to the n. And a alpha minus p1 alpha is bounded by r id theta minus 1 power n. And actually we can drop the a here, because these are positive. Oh, hold on a second. This doesn't add up. We've done something wrong. These r's should cancel out. Let me see. Okay, so they're supposed to cancel out. One of the two is supposed to be generous. To cancel out, we need oh yeah, okay. Yeah, okay, we do need to do it the other way. We need to because these have to cancel out, one of these has to be inverted. So we either pick, in any case, we need to show that this r could be arbitrarily small, is actually what we need. So that this rn can be positive, and then this one can go to 0 to cancel it out. So we do actually need to do what we did before. Okay. Okay. C and 0, coefficient series, blah blah. Okay. Okay, so we are going to be doing it this way. So we're saying find r greater than beta first, because that's the one that can't be generous. B greater than 0 such that beta n is bounded by that. Now find theta greater than theta alpha, which satisfies this. Finding such theta is possible since by the second characterization, every theta 0 has this going to 0, so there's a point n 0 after which this. So that this is that. Since for all n greater than we have this going to infinity, theta greater than theta 0 large enough so that rn theta is greater than this for the finitely many n with this, and then for n greater than or equal to n0 also we have absolute value p sub n alpha being less than rn theta 0, which is less than or equal to, or sorry, yeah, less than or equal to rn theta. Overall, this proves that Okay, so to summarize, we have, okay, so f is absolute value beta sub n as being less than or equal to br power n, and we find theta greater than capital theta alpha, iota alpha, such that p sub n, this will be absolute value p sub n, alpha is less than or equal to r n power theta. Equivalently, we have a alpha bounded by r id theta, and then we can say and by, oh yeah, okay, let's fix this real quick. Okay, so now find theta which satisfies this is strictly less than, instead of r, we'll do 1 over r. Finding such theta is possible since by the recursion, blah blah. Hit the point n0 after which has this strictly less than 1 over r, so that this is strictly less than 1 over r n power theta 0. Okay, I fixed that. Okay, so we're actually saying p sub n of alpha, not bounded by r n power theta, we're actually bounding it by 1 over r n power theta. And then to summarize, we have beta n bounded by brn, and then we find theta such that alpha is bounded by 1 over r n power theta. Equivalently, we have absolute value alpha is bounded by 1 over r id theta, and by subtracting off the first index, also a alpha minus p1 of alpha is bounded by 1 over r id sub theta minus 1. So we just subtract off the first index. Okay, there we go. Okay. Okay, this lets us bound f alpha like so, and then now we have the math. So f alpha will do a of f alpha bounded by, so we have a sum and 0 to infinity. We have absolute value beta sub n, and then we have a alpha minus p sub 1 alpha power n, and then we bound that with the sum n equals 0 to infinity of br power n, and then 1 over r times id sub theta minus 1, and then power n. Instead of doing 1 over r, we can just do r inverse. Okay, and then we extract out this b, cancel out the r's, n equals 0 to infinity. And we just have id sub theta minus 1 power n. Okay, and now here's where the magic happens. So since, actually, say, notice that, actually, yeah, let's do this last piece. So we'll actually have, instead of just doing id n power theta, this will be id theta 1 minus 1 o dot. That doesn't line up. Too much. Okay, we'll put a new line right here. Okay, so all we've done is, so we're calculating absolute value f of alpha. So we have absolute value beta, absolute value alpha minus p1 alpha. So again, this is just from this. F as a Taylor series. Beta n is, we apply the bound for beta n, we apply the bound for alpha minus p1 alpha as this. These r's cancel out, so we have rn here, and then r power minus 1 power n, so these cancel out. And then we factor out this b, and we just get id theta minus 1. Then we just notice, so id theta, if we just, id theta is itself id theta pointwise multiplied by this bold 1. So again, if we pointwise multiply by this bold 1 function, it's just 1 on every index, so just pointwise multiplying by it does nothing. And then as for the 1, if we have anything pointwise multiplied by 1, well, this regular unit 1 is 0 on every index except for the first one. And id theta is also is 1 on the first index, so this can equivalently be 1 is the same as id theta o dot 1. But now, since since id theta is multiplicative and o dot distributes over over products when one of them is multiplicative, then we can just pull this out of the exponent. And also, since o dot is continuous and linear, distributes over addition, we can pull this out of the sum as well. So I can pull this right out like that. And I'll do a bracket here just so that's clear. So we end up with this. But this is just a geometric series. This is b times, oops. So we have id theta, and then this is just 1 over 1 minus bold 1 minus 1, and then this just simplifies down to, sorry, this should be o dot 1 over 2 minus bold 1, and that's it, pretty much. There we go. That should be o dot there. Okay, so we've done all these bounds up to this point, and then this is where we start using our new machinery. So first of all, we take id theta, we pointwise multiply this with this. So this whole object here, it's 0 on the first index and then 1 everywhere else. And if we pointwise multiply that with id theta, that's going to be id theta on the first index and then 0 everywhere else. Or sorry, yeah, id theta 0 on the first index and id theta everywhere else, which is the same as id theta minus 1. And then because o dot is multiplicative, we can pull this out of this exponent. It distributes over products, so we get this. And then it distributes over sums, and it's continuous, so we end up with this. And then we just solve this as a geometric series. So this is this one, and this denominator simplifies to this. And then we're pretty much done. So in Appendix C, it is proven that we have the constant 1 over 2 minus 1 bold is in IBA sub n. So in particular, we have, okay, so in Appendix C, it's proven that this constant is in, sorry, not A sub n, this should be A sub theta. We could also just call this a lemma, actually, to make it clear that this is just supports this one theorem. Okay, in Appendix C, it's proven that this constant is in A theta, so this is, remember, it's this one. We proved that whole thing. So we have some actually, yeah, and since and it is also okay, in Appendix C, it is proven that the constant 1 over 2 minus hold on is in A theta, and oh yeah, this is why. Okay, so and we also have capital theta of iota, or rather, let's put it this way, iota id sub theta times o dot this 1 over 2 minus bold 1 this is just a sequence of n power theta times p sub n. Actually, we can just say this is just iota id theta. Look at this. So we also have theta of this whole thing less than or equal to theta plus, sorry, theta iota of this. And actually this is equal to theta plus theta of iota of this, which is less than infinity. And I think that's the completion. So in Appendix C, it's proven so that we have this constant in A theta. And in general, so we're just noting, if we do iota of this pointless product, it's the same as just iota x times iota y. So again, in the context of sequences, we just assume multiplication to be implicitly pointwise multiplication with multiplication. We can also do a dot here if we want. So we also have that this theta of this iota of this is just theta plus this. And this is finite since we have this in a theta. And that's it. So it follows from monotonicity and scale invariance of theta that theta of iota of f of alpha is less than or equal to theta plus this thing, which is finite, proving f alpha is in a sub theta. So that's it. So we've bounded it by this. So that is the theorem. So if we have alpha is an a theta and f is complex analytic at alpha, then f alpha is an a theta. And also, we specifically prove this specific inequality. So whatever value of theta we picked, we end up with this. Yeah, so that's fun. So that's that. So that's that one. I think we have time for maybe one or two more. I think we can upgrade this lemma to be more general. Okay, so we can say let's upgrade this lemma. Okay, so now we're going to say so this lemma was if we have a sequence in a theta which has a limit in a theta and it has an upper bound in a theta, then the Dirichlet series limit for a sufficiently large theta, these Dirichlet series will be convergent in some right half domain. So let me do this. Okay, so I looked at this one after last stream, and it turns out actually this is a lot easier to upgrade to this whole right half plane. So we're just going to say, so let theta be greater than theta alpha plus 1, or sorry, theta a plus 1. Then for each n in natural, we have this, we can say d iota alpha n s is this thing, and then we can say actually if we do a of this, and this is a, actually let's do it differently. D iota alpha is this, let's do a line and then we can say a of p sub k alpha sub n k power minus s. Actually, this shouldn't be, no, this is fine. Yeah. Okay, so we get p sub k alpha n k power minus s. If we do this, this is bounded by a of p sub k alpha sub n times a k power minus s, and actually this just ends up being absolute value of pk alpha n. Is that the case? Yes. And then this is bounded by, so absolute value pk alpha n is bounded by just a, so this will be pka times ak power minus s. And then we can say, since we can say capital theta of this sequence of k power minus s, the theta value of this k power minus s sequence. Why is this screaming at me? Oh, that's why. Sorry, the theta value of this sequence is just the real part of p sub 1 of s then so long as, actually we can say, so okay, so theta is greater than this for each n natural, okay, and then we can also say, and take, restrict. Oh yeah, actually that's fine. Is one of this, which is strictly greater than theta, plus, strictly greater than the theta, which is strictly greater than theta alpha plus 1. Actually, yeah, we don't need this. I was right before. This could just be equals. Okay. Since theta k power minus s k is p1, real part p1s, which is strictly greater than theta, which is theta alpha plus 1, then the summation sum across k of a, sorry, we'll do p sub k a times a k power minus s converges, which proves that the sum for d iota alpha sub n s is dominated across all n by, actually yeah, that's pretty much it. So so theta k power minus s, the theta value of this is real part p1s, which is greater than theta, which is theta plus 1, then the summation converges, so by dominated convergence we can swap the limits, and that just gives us limit as n goes to infinity of this is equal to the same limit n goes to infinity here, and then we can swap these limits. Here, and then this is just with alpha 0 without the limit, which we have is d iota alpha 0 with s, and we're done. Nice. Okay, yeah. So we take theta as being theta a plus 1, the upper bound. Then for each n, we have, actually this should be for each k. k and n. So for each k and n, we have absolute value pk alpha n k power minus s bounded by pk alpha n a k power minus s pk a absolute value k power minus s. Since this theta value of this is this, which is greater than theta, is theta alpha plus 1. Sorry, this should be theta a plus 1. Summation, actually we can say then the theta value of iota of, actually we can just say the theta value of the sequence in terms of k is strictly less than minus 1. So the summation converges. And theta this strictly less than minus 1, so the summation this converges, and Donny convergence lets us swap the limit. And then limit of d iota alpha s is just this limit of the summation. We pull this limit in, alpha n goes alpha 0, and then this is this, and we're done. Nice. Okay, so I think that's it. So so now we can do our last theorem. Actually, that's surprisingly fast. Okay, so we will finish this one off. So let alpha be an a sub theta, and f be complex analytic at alpha, then f d alpha is df alpha. Okay, so so to prove this, essentially this just relies on the previous ones. So we'll say for each n in naturals, actually we'll say let beta sub 0 equal f of alpha, and for each n in natural, define beta sub n as follows, and then we just have these partial sums. So beta, so we have beta sub n is defined as equaling the summation little n equals 0 to capital N of, actually let's do this. So yeah, okay. Let beta be in c power n0 be the coefficients of f, the Taylor series, where f centered at p1 of alpha. Now let alpha 0 be f of alpha, and for each n natural defined, and we'll do alpha sub n, and as follows. So alpha sub n is the sum from 0 to n. We have beta sub little n of alpha minus p1 of alpha to the power of n. Okay, so beta is in Cn0, coefficient of the Taylor series. Alpha 0 is f of alpha. For each n a natural, define alpha sub n as follows. And then we say, so we have alpha sub n going to alpha 0, which is f of alpha. Okay. Alpha n goes to alpha 0, which is f of alpha. Okay. Then we want to say, we can also bound Actually, let's do it. Okay, yeah. We can also bound the alpha sub n like so. So we have alpha value alpha sub capital N is bounded by, so we have this whole summation, and we can just say, just do absolute value of beta sub n, because beta are complex numbers, and then a of alpha minus p1 alpha power n, which is then in turn bounded by, if we just take capital N to infinity, okay. So we can say this upper bound does converge since, or sorry, this upper bound does converge, actually that's fine, does converge as a power series, and moreover, since a of alpha minus p sub 1 of alpha is in a sub beta, and this power series has coefficients norm beta n, which as complex numbers, then actually we can say, we'll define this as A. So this upper bound A does converge as a power series with coefficients norm beta sub n, which are complex. Does converge, actually we can say, as a complex analytic power series with coefficients norm beta n. And since absolute value alpha minus p1 alpha is in a sub theta, then also A is in a sub theta. So that's just from our lemma, f of, if alpha A is in a sub theta, so f of A is in a sub theta. So A is in a sub theta. So there is data in real such that all S in A re P1 greater than theta have the following limit. And so we have limit of n going to infinity. Actually, we can say capital N because we're doing alphas. So this will be d iota alpha sub capital N with S. This is equal to the limit, which is d iota alpha sub 0 with S. So we have this. Okay, and then we can say, however, since D is linear with complex coefficients, we actually have limit as this goes to infinity, so actually we'll start with this. This thing is this limit, which is by definition, so we have iota alpha n. So alpha n, let's do some brackets here. Okay, so alpha sub n, by our definition, it was just this partial sum. So plug that right in for alpha sub n. And that might be too long to fit on one line. It's not, but we do need a new line. Okay, so we get this whole thing, so iota, this, we can pull out these beta sub n's. Our linear actually, we can say, let's do it this way. Yeah, we'll do it this way, okay. Okay, so then we just have this whole thing, so we should still have this limit. This limit will be here. Okay, so we're going to drag out this summation first with the beta n. And then we can pull out this power. And see how that looks. Actually, okay, we'll keep the power in for just a second, because I don't want to go too fast. Okay, and this becomes let me think on this. So this should be alpha minus p1 of alpha, and then convoluted n times. Okay, actually, so what we need is this, which is okay. So we're gonna pull out that to infinity, and then this will be iota alpha minus p1, and this will be power n. Okay, yes, so d iota alpha s is this limit, which is this. So we just have this, we expand the definition, pull out the summation with the coefficients, a linear ring homomorphism and beta sub m are complex. So we pull out the betas with the limit, combines with the summation, and then we just end up with pulling all these out. And that is simply f of d iota alpha s. Okay, let's also, since that got cut off, let's separate this into another step. So this part in, so we end up with and so we end up with the summation. So actually we'll do iota alpha minus p1 alpha out here. Maybe just do this part in here. And then we end up with this. And that's it. Okay. Yeah. So instead of alpha 0, we can also do f alpha. Yes, so just to clarify, in the before times, we had proven this. So d mapping a theta to d is an isomorphism. We had proven this. Actually, we can maybe, we could actually maybe say, right here in this lemma, we could actually maybe improve this. We could say, my alpha n subset to a theta limit to alpha 0 with upper bound in a theta for all n, then actually we can say no, actually that doesn't help. Yeah, okay, that's fine. We just have this. And that's it. Yeah, so we have this limit condition, which lets us permute the sum of the product, and the fact that we have f of d alpha, or f of alpha is actually an a theta. So all of this is valid. So we formulate an upper bound which converges because it's an analytic power series, or complex analytic power series, converges in a theta. So this whole sequence is so basically we just have all these polynomials which tend to f of alpha. They have an upper bound in a theta, which means we can do this convergence of the power series. And the reason that these polynomials are important is because D is it's an isomorphism, or rather it has the homomorphism property. Has a homomorphism property in that we have it can permute with, actually specifically it's a linear homomorphism, a linear ring homomorphism. So it permutes with scalar multiplication with complex numbers, just can be pulled right out, and also if we have a product on the inside, a Dirichlet product on the inside, then we can pull that out as well as product on the outside, and likewise it's additive. So we just pull out these finite sums really easily. So we pull out the limit first. So this whole creating the upper bound is showing that we can pull this limit. So we have a limit of this f alpha. This is a limit of polynomials. We pull the limit out, and then this is just a limit of d of these polynomials. The sum comes out next. and then with the scalar coefficients, and then the product power n is pulled out as well. And then we just have minus p1 alpha, which is just a constant, and that gets pulled out lastly. Actually, we can see maybe a bit more specifically. Since D is a ring homomorphism, and D of iota z s equals z for any z in C, and beta n are complex, we should have yes. So we pull out the limit first, then we pull out the summation with the complex coefficients, then we extract the product, and then we just product out this last subtraction out to the outside, and then we have d iota alpha s, and then this whole polynomial is just f. It's just the complex analytic f. So f d iota alpha s, and that's it. Yeah. So that's the proof. So f d alpha is df alpha. That's pretty cool. That's sort of the big theorem of our whole, I guess, of this whole section and of a lot of this paper as well. It's a very nice theorem. Yeah. Okay. So yes. Okay, so I think we're pretty good. Okay, so the only thing we still need to do is we would like to do this theorem in the appendix, and we can also we would also like to at some point flesh out. We had a couple notes here, so we still need this. I'm gonna leave this note in here until I do that. We also had this that we were going to do that we haven't done yet. So we have this one, the one in the appendix, and then there's going to be one more section after the thing that we're working on. I think... Well, let's take a breather. Do you have any questions about what we've just done? Is there anything you'd like to look at again, or for us to go over? Because we definitely can. If there's any questions that you have with regards to what we had just finished. As always, I do not. Okay. All right, that's fine. I think this is, so yeah, this is pretty nice. Yeah, that would definitely be, I think, good. It's very interesting. There's a lot going on, especially in these later theorems. They get pretty complicated. I think this theorem in particular is very nice, because it means that, you know, if we have a complex analytic function, we can talk about, you know, if we want to talk about Dirichlet series, that in the context of analytic functions, actually we only need to think about what they're doing in the context of A, or rather A sub theta, even. It's very nice. It's very interesting. So there's a lot of stuff you can do with this. For example, any entire function applied to a Dirichlet series will generate another Dirichlet series. And of course, if you want to figure out the coefficients of that Dirichlet series, you can just permute the analytic function on the inside. So that's pretty nice. So like, for example, log of zeta, the log of the zeta function, that would be a Dirichlet series. And you could calculate its coefficients by taking the log of its coefficient sequence, which is the bold one. Or you could do any other thing. There's lots of other options to do. But anyway, yes, so okay. I think we can maybe do, I don't want to go too long. We can maybe do one more. We can attempt to do this one if we would like, proving that we have this theta value of this bold one. We could probably prove it in a similar way to this if we wanted, maybe. I don't think that's maybe what we want to do, like doing an induction. This is pretty lengthy. It's actually, theoretically, it's a lot easier to prove this. There's lots of proofs about this in the online and in various textbooks about number theory. Also, something, I guess maybe something to keep in mind just about this specific problem is that this is actually the divisor counting function. Because remember, if we have bold 1 times bold 1 at any projection, its evaluation is just the sum across divisors of 1 times 1. So just the sum across divisors. So it is the divisor function, which is interesting. An interesting way to think about it for sure. Yeah, if we want this, so proving that it's 0 specifically is definitely maybe a little more difficult. We wouldn't be able to do, I think we would not be able to do a summation technique like we did here. So here what we did was we took like this cumulative sum thing, and we showed that this had, you know, a certain growth tendency. I don't think we could do that here. There's some restrictions on the power of that, so that wouldn't help, I think, which is maybe a little unfortunate, or at least not immediately. The usual way involves breaking it down as a multiplicative sequence, actually. So this bold one, this is actually ID 0, so it has the multiplicative property. Bold 1 does. Although that being said, this property is not the fact that you know, multiplicative things are closed under convolution. That's not our Dirichlet product. That's not a thing we've proven yet. It is a thing we're going to prove in our last section that I would like to include. We'll get more into multiplicative and completely multiplicative things, but that won't be happening immediately. Yeah, so maybe alternatively we could probably just include a reference saying that yes, this is true, that this theta value is 0. This is a well-known result, so it's not necessary probably for us to put this in an appendix. We could just as well cite an outside source for this, which maybe we'll do. Anyway, well, if we're not going to do that, then I think I'm going to call it there for today, actually. Next time we come back, we will do, we'll do this one eventually, I don't know. Next time we come back, we'll start on the last section. It's actually a pretty interesting section. Actually, we can write the introduction right now, because I already know what it's going to say. This last section that we're going to write about is logarithmic subspaces. So by subspace we mean in the sense of like a linear subspace. So we can specify the linear subspaces of A are the subsets, or rather we can say are the additive subgroups its additive subgroups which are closed by under multiplication by scalars. Yeah, linear subspaces are additive subgroups which are closed under multiplication by scalars in, and we want to specify in the real number line. Or equivalently, they are the vector subspaces of C to the n when passed through the isomorphism iota. We define a logarithmic subspace of A as being a set, or rather we can say the image of a linear subspace when passed through the function exp. So a linear subspace is closed under addition and multiplication by real scalars. Since a logarithmic subspace is just the image of a linear subspace through the natural exponential function, so equivalently actually this is in a similar sense we can say such spaces are closed under addition sorry, that should be closed under multiplication. So instead of being closed under addition, they're closed under multiplication, and by exponentiation by powers in the real number line. So this is probably what we'll get to next time. So it's a very interesting concept to me, at least. This concept by scalars oh yeah, you're right. Okay, thank you. Yeah, so this concept is technically this exists in the context of just complex numbers instead of going all the way to A. So you could just take, so there are linear subspaces of the complex numbers. You have straight lines, and you have just the zero, and you have the whole plane. So the whole plane is technically a linear subspace. The one-dimensional, because essentially if you just treat C as being R2, it's the same. You have the lines, you have the plane, you have the one-dimensional lines, and then you just have the origin. Not very much variety. The logarithmic subspaces of C likewise are pretty limited. So you have all of C star, which is the complex numbers without zero. You have just the number 1 as a singleton. That's a logarithmic subspace. And also the straight lines of the complex plane when passed through the exponential function they turn into logarithmic spirals, which are very nice. They're very nice looking. There's some interesting edge cases, which is that, so, well, specifically I want to say they're logarithmic spirals which pass through 1. There is an interesting edge case, which is, you can have a logarithmic subspace of the complex numbers as just being the unit circle. So actually, let's do some visualizations. We've never done this, but this is fun. So we can say A equals 1, and then B equals actually 2, and then we'll do f of t is, I don't know how to use Desmos. It'll be e to the I a plus bi, which is sorry, e to the t times a plus bi, which is e to the power of ta times I think it's a point actually maybe we can just do this. Yeah, that's right. Okay, it's cosine of tb and sine tb. I think that's good. Then we're gonna do t goes from -10 to 4. Yeah, that's enough. Yeah, so these are the logarithmic spirals. So if this is the complex plane, so the x-axis is the real axis and y-axis is the imaginary axis, this would be a logarithmic spiral. And so equivalently, this would be one of the logarithmic subspaces of the complex numbers. It's closed under multiplication, under complex multiplication. Yeah, it's very pretty, isn't it? Yeah, so these are the logarithmic subspaces of the complex numbers, and we can just change our numbers. So we can change to b, or we can change to a, and these are all logarithmic spirals. They all pass through 1, and they are all closed under multiplication. They're all closed under complex multiplication. Very fascinating. So these are the logarithmic subspaces of complex numbers. There's a special case. So if we have a go down to 0, what is what notation? This one? Cosine tb comma sine tb. This is Euler's formula, if that's what you mean. So this is ETA. So we have t is going from -10. Actually, I can go -10 to 10 if we want. And then I've just multiplied it by a point. So this is multiplication right here. So ETA is the magnitude, and then this cosine sine is the direction. And then I've just added these. Yeah, it's multiplication. Yep. Yeah, so this is just a point. We could erase this, and then we wouldn't have a magnitude. And then actually that would be, it would just be a circle, because it doesn't grow. And it would just change how much how fast it's spun, but you can't see that on the thing. You can't actually see the thing. Anyway, yeah. So actually, I think, let me think on that, because we can actually do the linear subspace. We could actually probably do. We could just do it a different way. Equals, I don't know, 2, and then actually we can do p equals 2, and then we can do, instead of doing b, we can do sine t, and then this would be, b is still sine t, sorry, not sine t, it should be sine p, and then a should be cosine p. There we go. This is a lot better. Yeah, so these are now, let me also, I'm going to edit this. I'm going to go from, I don't know, minus pi to pi. That's a little better. So these are the logarithmic spirals. So we can actually do a little visualization here. We can do tp, sorry, t times cosine p and then sine p, and t can go from -1 to 1. Actually, we'll do 0 to 1. So actually, this is a nice visualization. So p is our angle. So as I change p, we just change the angle of this line, this purple line, and so this indicates the linear subspace. So equivalently, if we just stretch this out, the purple line is our linear subspace. So we just run through all the linear subspaces. And actually, we can probably limit this even further to just do 0 to pi. So this iterates through all our linear subspaces, and also in iterating through linear subspaces, we're excluding the 2-dimensional and the 0-dimensional case. Yeah, very neat. So this is the purple line is the linear subspace, and the green line is the corresponding logarithmic subspace. So we just pass it through an exponential function. So of course, if your linear subspace is just the real line, the corresponding logarithmic subspace will just be the positive reals, because you just get exp of the whole real line. It just maps to positive numbers. But you can also bend it around like this. So if the line is perfectly on the imaginary line, you get a circle. And so this is sort of the degenerate case. But for the other ones, you just get all sorts of different spirals. So you get all sorts of different spiral in, spiral out. It's very nice. So these are the logarithmic subspace. The spiral is the logarithmic subspace of C, of the complex plane. They're generated by, or they're the non-trivial logarithmic subspaces. So they're the ones that are neither 0-dimensional nor 2-dimensional, which is the minimal and maximal case. In complex numbers, that only leaves 1-dimensional cases, and you only have a one degree of freedom. So you only have 1 degree of freedom. In the context of our space A, there are infinitely many degrees of freedom. So if you exclude the trivial cases where you just have your linear subspace just be 0, or you have your linear subspace just be the entire space, you actually have infinitely many degrees of freedom in between. You have infinitely, not only can you do any finite dimensional vector space can be embedded into the space A, any finite dimensional real vector space can be embedded into the space A, so all of those would have corresponding logarithmic subspaces. But also you can have infinite dimensional logarithmic subspaces which are non-trivial. So you can have non-trivial infinite dimensional logarithmic subspaces, and there's a lot of variety there. But they generalize the idea of these curls, these logarithmic spirals, in a way that I think is very interesting. But yeah, so that's what we have to look forward to. We're going to formalize some of that. We're going to figure out what properties they have. And actually we have a really interesting one. The space of, not completely, so previously we had looked at completely multiplicative things, so A sub capital M. We won't be looking at this one, but we'll be looking at a very similar one, which is instead of having this property, so instead of having this property where for all n and k you get this multiplicative property, the space that we'll be looking at is where you only have this property for coprime numbers. So if n and k are coprime, so they have no divisors in common. And it turns out that space, so that, just to be clear, that space of sequences in A are called the multiplicative sequences, and these ones are called the completely multiplicative sequences. It's a bit confusing, but with the restriction that these are coprime, it turns out that the space of multiplicative sequences, if you exclude 0, so technically 0 would satisfy these conditions. That's why in this definition we've excluded 0 here. But in the completely multiplicative sequences space, that's actually a logarithmic subspace. So it's like one of these, except in the context of A. And what's interesting is that that logarithmic subspace. So here we sort of treated this as like a straight line here. So we have like a slope, and that sort of controls where our space is. So the logarithmic subspace is infinite dimensional. The one that we're going to be looking at for multiplicative sequences is infinite dimensional, and it's entirely situated above 1. So it has a trivial first index projection, meaning all completely multiplicative sequences are 1 on the first index. That's really interesting because it means it's completely impossible to visualize it, because if we were to project the space down to the complex plane, we just get 1. It's just the only one. And that is because the axes that it possesses are it possesses its underlying linear subspace, the one that you exponentiate to get the thing. The linear subspace is all the prime basis vectors, or rather, I think it's prime power basis vectors, or something like that. It's very specific, but it turns out to be a logarithmic subspace, and you can calculate its underlying linear subspace, and it's very fun. So that's what we'll do, and that's why I wanted to also to do this last section, because I think it's interesting, it's worth looking at, and it's very specific. It's just kind of a fun thing to do, and it's sort of mind-boggling to think about like exponential curves, but in a way that can't be easily projected down onto the complex plane, and they're in infinite dimension, and it's really strange. So that's something that's kind of neat, I think. Yeah. Anyway, so that's what we have to look forward to. So we will be looking at that. Yes. Yeah. Actually, now that I think of it, it's almost totally impossible to visualize these, because as soon as you exponentiate them, you just immediately end up with infinite dimensions. So it's not easy to visualize them at all. It's very hard. But yeah, so we have that to look forward to. So, but yeah. So, thank you for joining me today. I hope you had some fun. I hope you're excited for next time, because I am. I definitely am. And yeah, so I guess that's pretty much it. So we can just look at this spiral around. That's way too fast. Anyway, yep, so thank you for joining me. I will see you next time, and we'll do logarithmic subspaces. As always, if you have any questions, be sure to ask them. Yeah, it's very quick. As always, if you have any questions, be sure to ask them at any time that you are curious. You can always message me. But yeah, okay, thank you, and goodbye.